Thank you. So a concurrent snapshot is a data structure operating over an array of some length and consists of two operations, write and scan, where write writes a value to a cell in the array and scan copies and returns the array, producing a snapshot. Considering the following example, where a scan simply reads each cell of memory in order. Let the write 5 into the first cell, and then a scanner starts reading the first two cells. Afterwards, another writer writes 7 to the first cell, and another writer writes 6 into the last cell. After that, the scanner reads the last two cells and returns a snapshot of 5006. Linearizability, the de facto correctness condition for concurrency, holds if for any concurrent execution, there exists an equivalent linear reordering of events with the same inputs and outputs that respects a real-time order. That is, the order of non-overlapping events must be preserved in the linearization, while overlapping events may be reordered. So for example, the write of 5 must occur before the write of 6 and 7, while the write of 6 and 7 may be ordered either way in the linearization. This linearization is correct since the writes of the snapshot occur before the scan, while the write of 7 does not occur between the scan and the scan writes. Typically, linearizability is proven by establishing so-called linearization points in the program, where the program logically takes effect. However, establishing these points is in general a complex task. So, an alternative approach is to reason about the semantic relationship between procedures. For instance, a scan reads the values write wrote, which we here refer to as reads from. We will have multiple of these kinds of relations, and we will refer to all of these relations as visibility relations. And this was originally introduced by Hensinger, Segin, and Vafaidis, and used to establish actions for queues. And visibility reasoning is a declarative approach, unlike linearization points, which is operational, which allows for a high-level reasoning and facilitates for proof decomposition, modularity, abstraction, and reuse. We use these relations to reason about the inner workings of algorithms and develop axioms for snapshots. So if we adjust the example so the write of 7 happens before the write of 6, then if we try and linearize this scenario, we end up with a contradiction since the scan must have read 7, but the scan missed it and read 5 instead, which occurs before 7. So this means that we have an impossible snapshot, and the approach of simply reading the memory cells sequentially is not linearizable, and therefore we need a more sophisticated approach. And one such approach was introduced by Gianti. In this talk, we'll prove Gianti's snapshot algorithms linearizable, for which Gianti introduced 3 algorithms. And these algorithms are algorithms of varying complexity and restriction, where single writer means that no writers of the same cell may run concurrently, while single scanner means that no scanners may run concurrently to other scanners. Multi-writer and multi-scanner means that we do not impose the corresponding single restriction. And these algorithms have a shared invariant Gianti introduced, which we refer to as the forwarding principles, which are described which, which describe how to inform a scanner about a missed write, and are principles that guided Gianti's design. However, these principles are a bit concrete and only directly applies to the very first algorithm. So in this work, we provide the first axiomatization of Gianti's forwarding principles and modify the principles to an abstract form so that they apply to all 3 of Gianti's algorithms. We also provide the first axiomatization of what it means for an algorithm to be a concurrent snapshot, which can also be applied to algorithms other than Gianti's. We developed one shared linearizability proof that applies to all 3 of Gianti's algorithms, by showing that the forwarding principles imply linearizability. This is the first form of proof for all three of Jant's algorithms. Previously, only the singer-writer singer-scanner variant has been proven linearizable. This was by Del Bianco, mechanized in Coq, and by Jacobs, mechanized in Verifast. And this is the first application of visibility relations for proving internal invariant of a set of algorithms. And it is unclear if linearization points can capture this form of invariance. And this work also shows further evidence that visibility reasoning scales further than previously established by showing that we can apply visibility reasoning to snapshots and internal invariants. So for the rest of this talk, we will focus on Giante's first algorithm and the idea behind its correctness. We will formalize this idea, which are the forwarding principles, into the forwarding axioms, which the algorithms satisfy. And we build a more general set of axioms for snapshot data structures, which the forwarding axioms imply, while itself implies linearizability. So now we will describe Yante's first algorithm and forwarding. So this is Yante's first algorithm, the single writer, single scanner algorithm. The state of the algorithm consists of two arrays, one for main state of the memory and one for forwarding, which acts as a form of memory for repairing inconsistent snapshots. It also consists of a Boolean flag, which sets to true when the scan is running. The scans start by setting its flag to true, signifying that a scan is running, and it's followed by initializing the forwarding array. And it is followed by scanning the main array, and the flag is then set to false after that. And then the scan finishes by scanning the forwarding array for how to repair the snapshot afterwards. And write to the main memory so the scans can read the values. And if a scan misses a write, then if a scan is running, the write forward its value to the scan. So let's see this in action by revisiting our previous example, but now with Jant's first algorithm, where we again have a writer writing 5 into the first cell and a scanner starting reading the first two cells. And afterwards, a writer writes 7 to the first cell. But since the scan is running, it also forwards its value. And we have another writer writing 6 into the last cell, and it too is forwarded. After that, the scanner reads the last two cells, and this is followed by repairing the snapshot using the forwarding array. And this gives us a consistent snapshot, even for the problematic scenario. So in Jant's original paper, he introduced two forwarding principles. Don't worry about the text here. You don't need to understand this. So we will go more into detail soon. So these principles are very concrete and only applies directly to the first algorithm. For instance, the first principle says that suppose a scan operation misses as a write operation W because S reads AI before W writes in AI. If W completes before S performs line 7, then W will actually inform S of B by writing B into BI. So it is a bit concrete and applies mostly to the first algorithm. For these algorithms to apply to the other snapshot algorithms, we make them more abstract and generalized, and we will also simplify them somewhat. So these are the new abstract forwarding principles that we developed. We reformulated the original principles, and we maintained Jan's original intentions. And in our paper, we show how these principles correspond to the original ones. The first principle specifies what needs to happen when we have no observed forwarding, while the second enforces rules for when we do have forwarding. The first principle is more easily understood if we consider the contrapositive. That is, uh, if a write appears before a scanned write, but it's not visible in main memory to the scan, then the write forwards to the scan. In other words, we ensure that no write is missed. The second principle, we ensure that for a forward write, there's no new write squeezed between the write and the scan it forwards to, or its peers. This ensures that forward writes makes scans produce consistent snapshots. As we can see, the abstract form is easier to understand, and the formulation as axiom in mathematical notation will directly reflect this formulation. Also, these adjustments make the principles abstract enough to apply to all three of Yante's algorithm. In particular, since the algorithm will use slightly different methods of forwarding and requires slightly different definitions. So let's look at Yante's second algorithm. We won't go into details. We won't look at its forwarding. So for people interested, I refer to the paper. So this algorithm writes to and reads from the main memory like the first algorithm. However, forwarding uses its own forwarding procedure, where each writer runs this forwarding procedure twice. These forwarding procedures may then forward values of writes different from what the writer executed the procedure, so it can forward other writers' values. And we also look at Yante's third algorithm. This is the most complex of Yante's algorithms. Again, we won't go into details, so if you're interested, see the paper. And this algorithm functions similarly to the previous algorithm with forwarding. However, it has a more complex scan method, which allows for concurrent scanning, while multiple scanners run a single virtual scanner, which the real scanners read snapshots from. So again, it does have a slightly different forwarding, so we need a bit more abstraction here as well. Or abstraction helps here. So let us see how to axiomatize forwarding. So first, let us see how to formalize the visibility relation for Yante's first algorithm. So we will label the key operations of the algorithm with main, forward, and init. We denote visibility relations with labeled arrows, and forwarding of a write to a scan is defined in Yante's first algorithm if the scan reads the writes in the forwarding array, and the scan observes no forwarding of a cell I if the scan reads its own initialization value of the forwarding array. And this is note this is the particular definition for Yante's first algorithm, so each algorithm have their own definition. And a scan reads a write if either a scan reads no forwarding and the value of the write in main memory, or a write forwarded to the scan. And lastly, we say that the write is visible to a scan if the write wrote to the main array before the scan reads from the main array. We also need some additional notations for how events are ordered to one another. So consider the following example. An event returns before another event if the first event finishes executing before the other event starts. And we denote this with a square less than relation. And we say that another event happens before another event, which we denote with this triangle, if there exists a chain of returns before and reads from relations between the two events. In this scenario, we see that Wi happens before S, since Wi returns before Wi prime, and Wi prime is read by S. So to formalize the first principle, we first translate no forwarding into its notation. Next, we translate a write finishing before an scan write as the composition of returns before, happens before, or equals, and reads from. The read from relation creates a link to an scan write. Returns before ensures that the write finishes before the scan write, and happens before connects them. And lastly, we translate visibility to the corresponding visibility relation. For the second principle, we translate forwarding into its notation, and there exists no write such that the write does not occur in between the forward write and the beginning of the scan, which is expressed by the composition of happens before or equals and returns before. For the second part of the principle, the write does not occur in between the forwarded write and the pairs of the forwarded write, where the notation of the write before the pairs is identical to the composition from the first principle. And along with the forwarding principles, we have a total of 9 axioms for forwarding. 3 of them encode basic structure properties, and 3 encode basic forwarding relation properties. So let's axiomatize snapshots. We do this by specifying 6 axioms. We will focus only on 3 of them. So the first we will focus on is the core axiom, and that is that scans return the latest written value of each cell of memory. And formally, we express this by saying that there exists no write squeeze between a write scan reads from pairs. And additionally, to prove snapshot linearizable, we need some additional axioms. And one of those is that we have a total order on all writes of the same cell. And without this axiom, we cannot efficiently exclude all non-snapshot executions, since we would need an infinite number of axioms to deal with all non-linearizable scenarios. With enforcing some totality, we can effectively bound the complexity of specification. And another axiom we impose is the order of writes of different scans do not contradict one another. This ensures that concurrent scans can always be sequentially ordered. And the trickiest axiom to prove is the core axiom for snapshots. And we show that the forwarding principles imply this property. To show this, we split the read from relation and the happens before relation between write and scan into 2 cases each, which results in a total of 4 scenarios. The read from relation splits into non-forwarding and forwarding, while the happens before relation can split into these 2 cases with some case eliminations. We can now apply the forwarding principles, where for the first case with no forwarding, we just need to show that Wi prime is visible to S, which Wi prime happening before the beginning of S directly implies. Thus, for this case, we don't need any of the principles. Second case, we can apply the first principle to prove that Wi prime is visible to S. And for the third and fourth principle, we apply the first part of the second principle and the second part of the second principle. And the strategy for proving linearizability from the snapshot axioms is to in step by step grow the events closer to something being linearized. And this approach is adopted from Chakraborty, Ensinger, Tetjin, and Bavaidis, who proved their set of axioms for Q's linearizable. So we start with a total order on writes of the same cell, which expand in a consistent manner using the axiom into a total order of all writes. With this order, we build a latest event in time predicate that always lets us choose a latest event. And this allows us, by picking the latest event recursively, build a linearization order of all events. So, to conclude, we have shown that we can use visibility to simply and abstractly describe concurrent algorithms without using linearization points. We have shown that this method can capture deep properties of data structures like the forwarding principles, and we have proven 3 of the anti-snapshot algorithms linearizable by reformulating the forwarding principles abstractly and simply, and utilizing these to apply the single proof of linearizability. Thank you.